Okay, as mentioned before, I'm English, but I do tend to speak fairly fast at times. So please don't doubt to ask any questions and ask me to slow down a little bit. Okay, I'm working for Isoleika. We were involved in the development of the internal solution, the retrofit solution. This is an image from the cubic test center as well. Okay, so the objective of this solution is to offer an internal insulated facade system using the VIPs that can be applied in public buildings where the external version cannot be applied. As we'll see later on, there's occasions when it's not viable to use the external solution. The final solution that we developed is a continuous VIP insulation layer, and then a separate freestanding plasterboard solution. Okay, so the need for this technology. As mentioned before, there are buildings, and Liz also mentioned beforehand, where an external solution is not viable. Historical buildings which are protected from alterations on external surfaces. Also in cases where, and Rich mentioned, there's certain legislation in some areas which does not permit an increment on the external facade. Also there's cases where an external cladding may be very special. The Guggenheim, for example, you can't imagine applying the external solution. And so we need to find, in this project, an internal solution that could take its place. Okay, when designing the technology, there's a number of features that we had to take into account on designing. The first thing, the most important thing, is the VIP insulation loses all its capabilities if it's perforated. So one of the first things we're to look at is how can we protect this panel. One of the reasons that the VIPs haven't been used a lot in construction is this reason, that from going from 005 transmittance goes down to 023, so it's very similar to any other insulation. For that reason, we're to look how to protect the panel, not only in the transportation and the installation, but also in the use of the building. Obviously, an internal solution, during its use, people are going to nail a picture onto the wall. They're going to put up shelving, etc. Maybe there'll be new installations, plugs or sockets that need to be fitted later on. So we need to look for a solution to protect the layer of VIP. How do we do that? Well, on one side, the rubber protection, which was mentioned beforehand, was to protect it in its handling, in the transportation, handling in the installation of the system. On the other side, we wanted to create a buffer zone, a little buffer zone to avoid any future penetration of that layer. The other important thing is the hydrothermal performance of the solution. If we're going to have a continuous VIP layer, this is an impermeable product. It's not like other insulations. The moment we cover the whole of the internal facade with the VIPs, we're making it impermeable to vapor transmission. A building which beforehand breathed, the moment we insulate it, it's not going to be breathing anymore. So we had to look at how we're going to solve this problem. On one side, we have vapor diffusion, which is the vapour that comes from the interior of the building to the exterior. And the other point is that we're also creating a continuous, a very highly insulated surface, which, if we do have any gaps in that surface, we're going to cause cold points, which could cause condensation. So we had to look at including vapor barriers within the system on the warm side of the insulation. We also had to create a buffer zone to absorb any of the moisture from the inside. Another thing is when this type of insulation is installed, we should look at having a ventilated mechanical system on the inside, ventilation system, which will also improve any condensation problems. Obviously, thermal performance, the difference of the advantage of doing an external solution is it's a continuous insulation system. If we insulate from the inside, we obviously we can insulate on one wall, but where the floor slabs come in, where the walls come into that external wall, we're going to have a cold bridging effect. So the other thing we had to look at is a solution which also challenge those weak points. So we achieved that by actually bringing the insulation along on the floor level, on the horizontal planes, on the floor and in the ceilings. Also, obviously, the idea was to have a continuous VIP solution in the wall without any profiles, if possible. Obviously, any profiles, metal profiles, touching the wall would create cold bridging, and for that reason we went for a freestanding structural solution away from the actual VIP panel. And the other problem is the integration of existing services and future services. Obviously, existing walls will have a number of existing architectural elements and services. They need to be integrated in the design. We need to, at the moment of installing the system, we need to remove those systems and bring them out, and they don't penetrate and affect the VIP layer. Obviously, as we mentioned beforehand, any protrusion would affect the VIP. It could be perforated. So we need to make sure that the existing wall is totally free of all these elements. So this was another reason to create this buffer zone, this free space in front of the VIPs and the barrier, and the vapor barrier, which had enough depth to incorporate these elements. Obviously, the main objective here was to create a system which was as thin as possible. Obviously, we don't want to start making the system too large, otherwise we're not competitive with a standard solution. But at the same time, obviously, it's important to protect the VIPs, and to create this buffer space. Okay, so the solution, as mentioned before, is a continuous VIP on the existing wall, which is the red on the left here. We then have a freestanding standard plasterboard solution, where we also include a mineral wall within that space. Obviously, if we do have to create that space, when it's an advantage to also include an additional insulation. It also serves as an element of absorbing element within the internal, on the warm side of the insulation, to also protect from any moisture diffusion. We then have a 9mm thick OSB layer. This gives also greater rigidity to the solution, and also on any future fixings. This also protects the possibility of penetrating up to the VIP layer and perforating those panels. On top of the OSB, we have the a standard plasterboard. On the sketch on the right, there's a detail of how this continual insulation can also be brought inwards on the horizontal plane to reduce the thermal bridging on the floor slabs. So let's go through the different elements. We have the VIP insulation, 30 millimeters thick. So obviously we're reducing, compared to traditional insulations, we're talking about thicknesses which are very, very interesting. This is protected with, in the end, it's in the design process we used an asphalt lamination. This, in fact, we're actually working on changing this at the moment to look for a better solution, because some of the testing, the fire testing, has given negative results, and so we need to look for a better solution. But we're currently working on that. More than anything, this is the protection in the handling and transportation. Obviously, a nail, if a nail was driven into that panel, it would perforate. We then have a polythene vapor barrier adhered to the previous layer. Mineral wool insulation, which is within the profiles. Here we are, obviously, without having to make this layer too wide, we had to look for a solution that was freestanding. Obviously, if we had a solution where we had to tie the solution back to the external wall, obviously we're penetrating the VIP layer. So what we looked for was a solution for that could be mounted in a standard room, 3 to 3.5 meters high. The solution we found was using standard profiles, 46 millimeters, 48 millimeters profiles. We could reach 3.3 meters, doubling the profiles to form an H. There also are lots of manufacturers have alternative profiles, which are acoustic profiles, which can actually reach up to 3.65 meters. Also, the thickness of this was 46 millimeters, which is a decent depth to contain a electrical socket, and also to prevent any nailing going through to the VIP panel. We have the OSB 9 millimeters, and then plasterboard 15 millimeters, which is giving us an overall thickness of between 10 and 11 centimeters. Okay, so the main benefits, obviously, is the high energy potential. With this we can achieve U values of 0.15 watts meter squared Kelvin, and doing it with a reduced thickness. As I said before, we marked a maximum of 10 centimeters. In fact, with the obviously in reality, there's a little bit of a margin that we need to leave between the different elements, and it's a little bit over 10 centimeters. At the same time, we've achieved this thickness. At the same time, complying with the previous requirements mentioned beforehand. Okay. For the next slides, we're going to look at a little bit the installation of the system in Kubik's test center, and talk a little bit about the installation procedures.